for you guys to do really, really well, especially with a calculator and unit circle and all those kind of things. So, like if I click on the link to this review, and I'll even click the one that has the solutions on it. Evaluate sine of 4 pi over 3. Evaluate cosine of 11 pi over 4. Cotangent of 7 pi over 6. That, you know, just all unit circle stuff. Yeah, cosecant and tangent and things. Well, you have to be able to like y over x or 1 over x or whatever it is. Convert from degrees to radians. Convert from radians to degrees. A little, you know, domain and range of some trig stuff. And then, like, there's plenty of things on here that you can skip, okay? Like 11 and 12. But if you look through this, so link to the review with the solutions, or if you want to try it yourself first, which I think is good, right? It's the exact same thing, just not marked up. This is that copy that has the answers written on there. Evaluate trig functions, evaluate inverse trig, some domain and range stuff. Given the sine of 2 trig functions at some angle, sorry, at some angle, there we go. And what quadrants does theta lie? So like sine is positive and cosine is negative. Sine is positive and cosine is negative. Oh, we're in this quadrant over here. Things like that. Reference angles. Literally, can you locate an identity on the cheat sheet? Basic transformation stuff with phase shifts. You know, well, here's an equation. What's the phase shift? What's the amplitude? Things like that. Yeah.
So you said it was like our unit circles.
Absolutely. So that trig cheat sheet, the two-sided thing, has a copy of the unit circle. So I think if you bring that, you'll be good. I think that's really kind of the only thing you'll need to bring with you, of course, besides a device of some kind that you can do this and only this, and then calculator of some sort if you need it to help. Okay, last one, solving basic trig equations. Like, let's pick one. Let's pick a nice one. It's definitely, like I said, some things in here that we just didn't get to, and that's okay. But like, identify the phase shifts. Here's, amplitude of 4, period of pi, and a vertical shift. Which equation is right? I want to show you one that has solving the equation. I didn't see one in the multiple choice, but plenty of things in here that we just haven't done, and it's okay because they're not going to show up on the final. So don't have to worry about it. Solve the equation, right? Set it equal to 0, factor and solve, but it might even be even simpler than that. Yeah, calculator stuff we don't have to worry about with law of sines, law of cosines. That's all old geometry stuff, so we're good there. Area of a triangle, don't worry about. Yeah, so nothing too crazy. But there is one thing that is new, and that's what I want to teach you today. Okay, and between today and tomorrow, what I'll try to do is I'll go back through that list of topics and create kind of additional practice problems of each kind. So if you feel like, oh, the one from the review that looks at this topic, that's not enough for me to feel like I get it. So that's what I want to do for you. They gave us a review, so I wanted to kind of lean on that a little bit, and then anything else that I felt like would be worthwhile, I'd like to do with you kind of like today, tomorrow. So the thing that I have to show you is relatively straightforward. It's just new, so we haven't done it yet. But there is one thing that I want to do to finish up chapter 3 since we just never got to it. So take out those guided notes. I want to just add one little thing. Like I said from before, I want to give you the rule for inverses in case it comes to it. Okay, so take out the guided unit 3 guided notes, and we're gonna go really quickly to page 226. 226. Right after this, like, I'm not even gonna practice. I just want you to have it so you know. Right after this, we'll jump into our notes just separately. Like jump into kind of a blank sheet of paper, and I'll teach you the rest. Let me get. There's gonna be some Precalculus stuff. We're gonna get that going here in a second. Okay, so 226, you'll have a spot right here. Pull this up. Okay. Actually, that talks about what an inverse is. I'm pretty sure we know what that is. Go to 227. Sorry. Okay, and in this first box, right, this f of the f inverse of x, this is how we would like prove what the derivative of an inverse is. But the idea with this whole setup is they have to like give you the function and the inverse, or they have to give us like the function or the inverse, and then we have to find it. Because what you'll see is part of, to find the derivative of a function's inverse, you actually have to know both of them. And so the thing that we're not going to actually like go through the process of differentiating both sides. You know how you can like square root, add, subtract, multiply, divide? I can take d dx of both sides. We can differentiate with respect to x with an entire equation. And what it would do is it would get us, just like I said, I just want to kind of give it to you. And we'll use this version, okay? That is the rule. And that's what I want you to write in that box in 227, okay? Given some function, right? Y equals some function of x. And its inverse, okay? F inverse of x. What we can figure out is we can figure out the derivative of the inverse. Because the derivative of a function, just whatever my normal rules are, right? If I know what the derivative is, I'm good to go. So f inverse prime, the derivative of the inverse is just 1 over and then a composite function. The derivative of f, whatever the rule is, of, and then you put the inverse in for x instead. So like, for example, in case you just want to see one or kind of jot this down, okay? So, for example, okay, if we had some function, right, some f of x, and we'll keep it simple, like 2x plus 1. Okay, let's say that was our function. All right, we wanted to figure out what the derivative of the inverse is without actually finding the derivative of the inverse. Like without actually like going through the process of finding the inverse and taking its own derivative. Well, the issue is that I need to know what the inverse is first. Okay, and that would be, right, switch x and y, solve for y, like old algebra 2 stuff. And maybe you could see what that inverse might be just kind of by looking at it. But like imagine switching x and y. So x and f of x, right? So there's a y right here. Just have to solve for that. I would subtract 1, divide by 2. All right, so I would eventually get, x minus 1 over 2. That would be my inverse. So you have to know both of those parts. If I wanted to figure out, so this is kind of continuing from there. If I wanted to figure out what the derivative of the inverse is, it'd be 1 over f prime of the inverse. Meaning, okay, what's f prime? Just by looking at this, 2. Okay, 2 times. Okay, x minus 1. And it's just not something that we, like, it's so rare that we actually ever use it. That's why I'm not going to stress about it, but I just wanted to have an example to look at. Okay. That's not something that I'm going to need in Unit 4. We're not really going to look at stuff like that. We're not going to come back to this in like BC very much. We don't really use it a ton. It's just that maybe finding the derivative of the inverse is tricky for whatever reason, and we can just kind of put them together. So Just wanted to give that to you so that you can see. Okay. And this is kind of what they were talking about, how to do it. You can take d dx of both sides of an equation. You can differentiate the left side, differentiate the right side, and then kind of go from there. Okay. But what we're going to do is we're going to put that Unit 3 stuff away because, yay, Chapter 3 done, good to go. And I'm going to teach you one quick idea in trig that we never got to because it was all the way in Chapter 9. Precalc textbook. Hi there. Thank you. So while you get yourself to a clean sheet somewhere, just to show you what we did, right? Chapter 4 Precalc was basic trig stuff, right triangle trig, unit circle, things like that. Chapter 5 was all about analytical trig, so that's where we did identities and solved equations, maybe using identities. That's where sum and difference came in. We never got to multiple angles or product of sum identities, but you can certainly do that with sine of 2 theta being sine 2 sine of theta, cosine theta, things like that. Chapter 6 was an entire trig chapter as well, but we did the first 2 in geometry, right? Law of sines, law of cosines. Vectors we never got to. That's a good thing to have a little bit of background in. Does anybody know what a vector is? Has anybody taken physics? Yeah.
It's a arrow with direction.
It looks like an arrow. Yeah, we draw it like an arrow. It's a line segment with direction. It's a directed line segment. That's all a vector is. It just looks like, I gotta get past law of sines, law of cosines. There's law of cosines. A directed line segment. It has a beginning, it has an end, but it just has direction. We're just gonna go this way, and we draw it kind of like that. It's got length, which we call magnitude, and it's got a direction. That's all it is. Okay, just kind of tells us where things are headed. Okay, but we don't have to stress too much about that because we're not going to worry about vectors. But you'll see that in physics. You'll see that come up a little bit. And then there's stuff that we can do with it, right? We call it vectors in a plane because we're just going to draw them on a piece of graph paper and measure them. All right, a lot of trig stuff that comes into that. We can do something called dot products. We can have 2 vectors being multiplied together. And there's a trig form of complex numbers, which is a really, really fun one. But you'll get to that later for sure. 7 is matrices. Have you guys done anything with a matrix before, right? So 7 is all about matrices. Basically a great way to solve linear systems. And you can do them in multivariables. You can do inverses and determinants and fun stuff like that. That's why there's an entire year-long course for this, because there's so many things we could do. Sequences, series, probability, binomial theorem, ways to count things faster. Sequences and series, Calc BC, you guys will see that in Calc C. Okay. Fibonacci sequence, geometric and arithmetic sequences, and kind of fun stuff like that. But what we're going to talk about is something that happens in Chapter 9. Okay. And this is something that is a big part of a regular pre-calc year-long course, but something that we just do not get to in honest pre-calc because we go as fast as we do. And it's about certain shapes. Okay, a big part of the first 3, circles, parabolas, ellipses, hyperbolas, rotations of conics, and things like that. Okay. Where you just kind of look at different shapes that you can make that are kind of circular. Things that could be cut. This is actually kind of cool. Might be a little hard to see. Darken this up. We call them conic sections. Let me turn the brightness down here so you can really see what's there we go. That's better. So imagine 2 cones kind of stacked end to end. And you take a piece of paper, or you take a knife, and you slice through the cone. Well, if I slice through it perfectly flat, it's going to make a circle. But if I slice through it at an angle, right, one of those lengths, one of those sides is going to be stretched out a little bit, and we're going to get an ellipse. If we cut through it, but we cut through the open side, we'll get a parabola. And if we cut through it straight down, we get a hyperbola. And all those conic sections are really, like there's a lot of math that happens behind the scenes with conic sections. And you probably did some circle stuff and obviously some parabolas, but there's more to a parabola than you probably realize. You just probably think like x squared and stuff like that. There's actually a lot more to this conic section. It has a lot of good engineering applications. A lot of things that are parabolic have a lot of reflexive properties and things that we can use. So there's an imaginary directrix and there's a focus in the middle and all sorts of cool stuff. But we're going to skip all of that. And what we're going to look at, okay, is something in section 9.5. Okay, and so if you're going to title this page, okay, let's call it polar coordinates. Okay, now the concept is not super crazy. Okay, and once you get the hang of it, I think you'll find it relatively easy. What we're going to do is we're not going to graph in the way that maybe we're normally used to, where we graph on a piece of graph paper that's made up of a bunch of squares, right? And every square is a rectangle, right? So not every rectangle is a square, but every square is a rectangle. And so we call that rectangular coordinates, okay? We have something, and I'm just going to fast forward here to 9.5. I think it was page 36. 30. Well, that was the section before it. There we go. Okay. When we start talking about polar graphing, we're not graphing it in a way that maybe we're as used to seeing. You know, you take a piece of graph paper, what do you see? You look down a bunch of squares, right? And everything's the same length. And the way that we measure rectangular coordinates is an x direction and a y direction, right? Let's take a linear path left to right. Let's take a linear path up and down, and that'll end us at wherever this buried treasure is at some point, some xy, right? When we graph things that are polar, okay, and we graph in the polar coordinate system compared to the rectangular coordinate system, okay, it's still two dimensions. There's still a center. It's just that emanating from that center is not a collection of squares. Instead, imagine this, okay? Floating out in space, okay? And you can look directly down at the North Pole, okay? Now, of course, Earth isn't perfectly spherical, right? Because the rotation of the Earth kind of squishes it out at the equator, right? The diameter of the Earth from the center is a lot longer than pole to pole. But imagine it was, right? Imagine looking down at a sphere. And what's drawn on the Earth for us is all of the lines of latitude, right? 90 degrees up at the top, and then 89, 88, 87, 86, kind of working all its way down, okay? Imagine that this right here is you looking down on the North Pole. And what you can see coming out of there, let's see how well I can do this, are all of the lines of latitude opening up. Can you picture that? Right, looking down on the North Pole, and if those are perfect circles, right, looking down on the North Pole, and you can kind of see like every circle that makes up a ring around the Earth kind of making its way out. But imagine that it just keeps going. It doesn't come back around. There's no perfect sphere. It just keeps getting bigger and bigger. And when we start talking about naming a point on this plane, I guess, right? I'm not going to name it XY. When I draw a point, say, I don't know, right here. Now, sure, I could call it XY. But the problem that I have is that I don't have like a linear measurement system to do it because my axes, the way that I'm drawing out the space between my axes is not made up of a bunch of straight lines. It's made up of arcs, circles, going around and around. And that point right there is much easier, much more easily described, not by saying, hey, let's go over 3 and up 5 to get there, but describing a different path, a different way to get to that point. And maybe you might think it's more direct, maybe you think it's less direct, it kind of depends on what you want to view this as, but what do you think? What could be a different way for us to get to that point from the center? Because remember, when we start talking about like getting to a point, it's let's go left and right, let's go up and down, however far you want me to. Okay, cool, now you're there. What might be a different way to travel from the center along a red pathway? Remember, X, Y, we travel left and right, we stop, and then we travel up and down. Exactly, right? Straight lines only to get to a point. That's rectangular. That's why it's called rectangular. Describe a different pathway, and let's say, hey, like this is a circle with a radius 1, a radius 2, a radius 3, a radius 4, something like that. Kind of making its way out. How could you get from the center to that blue point, do you think? Traveling only along anything in red. Laura, what do you think?
Go either up or across, and then once you get to the point where the circle touches the axes, you like follow the line.
So you take a path either like along the x-axis or along the y-axis, and then stop at a spot where like that circle intersects an axis, okay? And then what?
And then follow the red line.
And then follow the circle. Okay. Now, when we've gone before, we usually go left and right first. Let's do that first. Let's always go left and right first. So they kind of say, okay, that's way bigger than I thought it was going to be. All right, let's travel along this way. And then follow the circle. And once I get there, I'm there. I made it to that point. Okay. So what did we do then? Like, how could we describe the path that we took? That's humongous. I don't know why I made it so big, but how could we describe using, like, instead of X, Y, think about like how this graph looks and what you did to get there, to take a path, just like let me get to the right circle, and then let me kind of travel along that path.
You do R, comma, and then that R point.
So R, the radius of the circle. Okay, I like that. Whatever radius I took, which is really like, I'll draw it in blue, I guess. Like it's really that, right? It's the same length. That R is the same as the green R that we took to get there. It's all one circle. So it doesn't matter how I travel along the radius. But you're right. Let's take a path in the R direction. Right? Let's find what circle we're on, and then measure the arc length. Yeah, that's like how far we've traveled, sure. But won't that distance be different depending on what circle we're in? Right? If I'm in a circle radius 1 and I want to get to like this point right here, or this point right here, or this point right here. Let me pick a different color, right? You've got this purple point right here, this purple point right here, this purple point right here. If we measure the arc length, it already kind of depends on the circle that we're in. So I feel like maybe we might be doing a little extra work to like measure the circle twice. Is there a different way to describe how to get to any of these points along that line right there? It doesn't matter what circle we're in.
Angle.
The angle. What do we use for angles? Okay, this xy is rectangular. Okay, that says rectangular. That system right there where we move in straight lines is xy. When we talk about polar coordinates, it's still in 2 dimensions, so I really just have to take 2 paths. It's just let me go a distance of r and then open up an angle. That's what it is. Okay, that's polar coordinates. Okay, and it can be a really, really useful system to do a lot of cool graphing once we get into it. There's a lot of things that we can create in the polar coordinate system that are really hard to create in the rectangular system, and that's why it's pretty fun to kind of look at and play around with. So, what I wanted to teach you to do is balance between the two. Okay, and that's one of the questions that you're going to see come up is give me a rectangular point, write it in polar, or vice versa. Okay, and the connection that I think we need to see is like, how do I get to that blue point normally? Okay, so that if I was drawing this in the rectangular system, right, and I've got a point, okay, whatever, it's over here, right? Some x, y. What would be a good way to measure the radius that got you? So that would tell us how steep the line is to get from the origin to xy. I want to measure the distance. I want to know how long r is. Slope is good for sure, right? That's going to be super important for us calculus-wise. But we need to first measure r first, right?
It would be the distance to x. Right?
Nice, right? We just want to we want this distance right there. So how do we measure it though? If I know x and I know y, right? It's 3, 4 or something. How do we get to a length for r? Yeah. Okay. R squared equals x squared equals y squared. Okay, which means r is the square. Right? It's a right triangle. And that's what's nice about the rectangular system is everything happens at perpendicular angles. And we can use that right away. Okay. So you give me something rectangular, I can find r. I'll just do the square root of x squared plus y squared. And now I can use that formula. I never have to derive it again. That thing that's boxed in there, we're going to use that. Absolutely. We're going to figure out what the square root of x squared plus y squared is. And I don't even need the plus or minus because it's r, it's a length, so we're taking the absolute value of it anyway, so I just have the positive version of the square root. So give me an xy, and I have to find r theta. Boom, there's r plus. How are we going to find theta right there? If the only thing that we know is xy. Now, sure, we could solve for r, and we'll do that as part of it. But maybe save ourselves a little bit of trouble and only use xy trig functions, right? It's right triangle trig. And so which trig function only has x and y in it? Tangent or cotangent. We'll just use tangent because it's simpler, right? What we've got is that the tangent of theta is y over x. So what's theta? The inverse tangent. There you go. if you want to go from rectangular to polar, we'll do both of those things to get there. You give me a point, some xy, and you want me to write it as a polar coordinate, we'll do those two things, okay? So let's try. Before we even worry about going back the other way, let's make sure that we can go from rectangular to polar by doing those two things. And sometimes that tangent is really nice, right? Sometimes it's a perfect unit-circle spot, right? It's pi or pi over 2 or 3 pi over 4 or whatever. Sometimes it's not, right? Because nice right triangles don't always make really nice angles. And that's why we have radical 2 over 2 and 1/2 and radical 3 over 2s and things like that. If you get a nice tangent like that, sweet, then our theta is really nice. But if you don't, okay, inverse tangent of 3/4 or whatever it is. That's cool too. Okay, so check it out. Let's say we are given the point 1, 1. Right in polar coordinates, right as a polar coordinate. Either one's good. Okay, so this is x, y. And what we want eventually, once we're done, is r theta. Like, what circle are you on to get there? What is the radius of your circle that you're on if you're at the point 1, 1? And what angle do I have to open up? Like a regular angle coming out of the, coming out of the positive x-axis, right? So there's a point 1, 1. We're here. And we want to try to figure out, okay, what is the right circle for me to get to? Like, is it 1? Is it more than 1? Is it less than 1? And then what angle do I have to open up to get there? Let's start with R. What is the formula to find R? What did we just figure out? Came from the Pythagorean theorem, right? This one. The square root of x squared plus y squared. Every time. If you give me xy, I just have to do that. Okay, so the square root of, and we'll write it out first time, learn this. This is new. Not hard, but still new. X squared plus y. 1 squared plus 1 squared. So what does that equal? Square root of 2. Which makes sense because this length right here would be the square root of 2. All right, 1, 1, radical 2. Now, maybe you can look at this and know what theta is without actually having to do the work. But let's check it out, see what we get. What we figured out is that it was the inverse tangent of y over x. And if you're not great with evaluating inverse trig, that's what your calculator can do for you. It's just going to be the inverse tangent of 1 over 1, which is the inverse tangent of 1. And we're just trying to figure out what that angle is right there to open us up to a point that's at 1, 1. And by deciding what r is, doesn't matter what circle we're in for theta because we already established how far away from the origin we're going to be. Does anybody know? What's that? 45 degrees. It's so 1, 1, radical 2. It's isosceles. It's got to be 45 degrees in there. So radians though. What's 45 degrees in radians? 5 over 4. Okay. So this point right here would be radical 2, comma 5 over 4. Questions? Yeah. Let's try another one. Okay. We're going to give in a point. Let's say -5, 0. Okay. And again, this is rectangular. Meaning we're in that regular Cartesian plane where we've got squares all over the place. All right, let's go left 5 and then up and down 0. And what we're trying to figure out is what the polar coordinates are for that. And eventually what we want to get to is r theta. So if we can figure out what r is, if we can figure out what theta is, then we're done. We just read it as a set of coordinates. For me, I find it always really, really helpful to just draw it out. There we are. There's the points that we're trying to get to. I just want to know what circle am I on, and then from standard position, how far do I have to open up an angle just to get there? So really, the question is, okay, how far are you from the center? That's all r is what distance does it take to get there right away? I don't want to go left and right and up and down just to get there. I want to go straight there. And that's what I kind of like about polar. It's like, get me right to the point. All right, at least onto the right circle. What is that length? Without having to really do it. 5, right? Now, we can prove it, right? I can say, okay, cool, this is -5 squared plus 0 squared, which is the square root of 25, which is 5. But you draw it out, you might be able to get yourself to that number really, really quickly. Cool. This length is 5. Again, theta might not be something you have to like actually do the inverse tangent for. Just open up the angle, figure out where you are. If you can look at that picture and say, okay, I know what that arc's going to be. If I wanted to draw that theta, can I figure out what angle that is in radians to get me there? What is that? Pi. Done. Now, it is the inverse tangent of y over x, right? The inverse tangent of 0. Plug that in your calculator, see what you get. Lo and behold. Make sure you're in radians, if you want to be in radians, which is what polar coordinates are in. If you're going to leave your calculator in degrees because you don't want to get like 2 pi over 3 as an answer in decimals, you want to know what your angle is, you can stick with degrees. Oh, cool, 2 pi over 3, nice, 120 degrees, and then make the switch. Okay, but polar coordinates are in radians. 5, 5. That's the direction they're going to ask us to go on Friday. From rectangular to polar. Okay. They're not going to have us go back the other way from polar to rectangular. Now that I've said that, let me just be sure. Yeah, okay. But I do want to tell you what the conversion is, but I want to focus on this. I don't want to fill us with too much. So I'm going to give you the other way. We're just not going to use it today. And then I'll give you a couple like this to try to make sure you can practice it, and then we'll be done. And then tomorrow will just kind of be like an overarching review day for all the trig stuff. Okay. So you know rectangular to polar. Now let's go polar to rectangular. Okay. Meaning I'm starting in r theta, and I want to end in xy. And it's actually really, I think it's even easier than going the other way, which is why I think they probably asked us to go the way that they did. It's really easy. R cosine of theta our sine theta, right? X is cosine, y is sine, so that makes sense. Just have to multiply by r to figure out what circle we're on because we're not necessarily on the unit circle. Done. And there's a ton of stuff that we can do with it. It's really, really nice. I want to show you some cool stuff. I'll leave that up there for a second. I'll get this going. And the I know I talked about it briefly in one of the previous sections that I just kind of went over, telling you all the things that we missed. But I talked about the trigonometric form of a complex number. It uses those two. So nice. My goodness, I love it. Okay, here's the cool stuff that we can do. This is the part that I really like. The whole section on polar coordinates gets really interesting, and then we get to like graphs of polar stuff. If you go to Desmos on the left-hand side here, you can actually like press the menu and open it up. And they have like lots of examples of stuff, right? Okay, let's look at parabolas and mixtures of these. And here's the cool stuff that we can make in the polar system. You cannot do that in rectangular. It's not something that we can do. I cannot graph something that looks like that. At the polar rows, the logarithmic spiral, right? Kind of looks like the Fibonacci spiral. I don't know if you guys have seen that. The golden ratio. I have a ton of really cool things that we can do. So, have a good day. I'll see you tomorrow. Thanks, everybody. What's up, Xander?
What's up, Carl?
How we doing?
Wow. How you doing, big man?
We're gonna leave this one up so it's pretty. You're welcome. See ya. Thanks, everybody at home. Have a good day. See you tomorrow.
Thank you. Have a good day.
Bye.